What's inside Jupiter's core? Think you know Jupiter? Think again. For decades, scientists argued over what the core of our biggest gas giant was like. Was it solid or missing altogether? Then in 2017, NASA's Juno mission made that debate irrelevant overnight. The data from Juno suggested both sides were wrong and revealed a third option no one expected. Jupiter's core isn't solid, but it isn't absent either. It's fuzzy. And that's a problem, because it upends everything we thought we knew about Jupiter's formation, its interior, and even its bizarre magnetic field. Join me today as we uncover exactly what Juno found, explore how a fuzzy core could form in the first place, and reveal why this changes how we think not just about Jupiter, but gas giant planets everywhere. Picture this: a colossal world, swirling with storms bigger than Earth, hiding secrets deeper than any ocean. Why does it matter? Because understanding Jupiter's heart could rewrite the story of how our solar system and countless others came to be. Stick around, because by the end, you'll see why this fuzzy mystery is one of the hottest topics in space exploration right now. Let's rewind a bit. For decades, two competing theories dominated the scientific conversation around Jupiter's core. On one side, many supported the gravitational collapse theory. Imagine a vast cloud of gas in the chilly outer solar system, collapsing under its own immense weight. No solid starting point, just pure, swirling chaos turning into a planet. In this view, Jupiter would have formed directly like that, before drifting inward to its current spot. The result? No core at all, just layers of churning hydrogen and helium, stacked like a cosmic layer cake all the way down. It's a clean, elegant idea, right? But not everyone bought it. The other camp was convinced Jupiter kicked off with a solid core, packed with heavy hitters like carbon, nitrogen, oxygen, magnesium, silicon, and iron. Picture a rocky seed growing fatter and fatter in the nebula's icy fringes. Its gravity ramps up, snagging hydrogen and helium like a magnet pulling in filings. Over millions of years, that swirl builds the behemoth we know. This core accretion model feels intuitive. It matches how we think planets bootstrap themselves. Solids condense first out there in the cold, then gobble gas as they migrate sunward. Models predicted a sharp-edged core, maybe 10 to 20 Earth masses, neatly walled off from the fluffy outer layers. So which was it? Early probes to Jupiter, Pioneer, Voyager, took swings, but they couldn't punch through the clouds deep enough. By the 1990s, though, things sharpened. Galileo dove in, sniffing out heavy elements galore, way more than hydrogen and helium alone could account for. Fun fact: Jupiter's got about 1.5 times Earth's worth of those extras locked in its depths. Galileo also spotted clues to the magnetic field, generated by liquid metallic hydrogen churning inside. But wait, if the core's all liquid, how did gas capture start? Planetary formation demands that solid nucleus to kick things off. Did Jupiter have one and lose it? Or are our gas giant blueprints busted? Missions piled data, yet the core stayed elusive. Gravity maps were fuzzy, literally too coarse. Was it compact rock or a smeared-out haze? What fueled that wild magnetic roar? The debate raged on until Juno flipped the script. Fast forward to August 5th, 2011. Cape Canaveral hums with energy as NASA's Juno blasts off, a sleek spinner of science aimed straight at Jupiter's secrets. Its mission? Peel back the layers on composition, gravity, and magnets with laser precision. 100 times sharper than Galileo's best. No half measures here. Juno slips into a polar orbit on July 4th, 2016. Independence Day irony not lost on anyone. Its path? A daring ellipse, dipping to just 4,200 kilometers above the cloud tops, then swinging wide, over and over from every angle, like a cosmic MRI. Why gravity? It's the ultimate interior spy. We've all seen those rubber sheet demos, mass warp space, pulling things in. But planets aren't perfect spheres of sameness. Jupiter's a mosaic. Dense rocks here, lighter gases there, all jumbled. Those imbalances ripple the gravity field, subtle as a whisper. Juno feels them as tiny speed tweaks. 0.01 millimeters per second, folks. That's finer than a heartbeat. Meanwhile, it pings radio waves home. Doppler magic. Stronger pull blue shifts the signal, weaker reds it out. Stack those reads and boom, a high-res mass map blooms. Galileo sketched outlines. Juno carves details. And the core reveal? Mindbender. No solid ball, no void. Instead, a dilute fuzz, bleeding into hydrogen layers like ink in water. No crisp edges, just a gradual fade. It sprawls huge, maybe half Jupiter's radius, 20,000 kilometers wide. Heavy elements taper off smoothly, not slam-dunked at the center. Published in Nature in 2021, this flipped tables. Suddenly, formation tails needed tweaking. Was it a smash-up? Slow build? Juno's still orbiting as of 2025, its extension wrapping up this September. But the data's already reshaping solar system lore. Rhetorical question. If our biggest neighbor's core defies basics, what else out there waits to surprise us? Okay, deep breath. How does a fuzzy core even happen? Early post-Juno buzz pointed to drama, a baby Jupiter smacking into a protoplanet, shattering its solid heart and mixing it into a hazy soup. Up to half the core from that wreck. Poetic, right? Like a stellar car crash forging a new beast. But hold up. Supercomputer teams dove in, cranking scenarios. Vary impact speed, angle, proto-Jupiter size. Run the sims. What do they get? Shake, rattle, and settle. Dense rocks plunge, then sink back like sand in a shaken jar. Boundaries reform sharp as ever, no lasting blur. It didn't match Juno's smooth gradient. Back to square one. Then, 2025 drops a bombshell. Researchers from Durham University, NASA, SETI, and Oslo, armed with the Dirac Cosma supercluster in Swift code, rewrote the script. No cataclysm needed. That fuzzy core? It bloomed gradually as Jupiter gobbled rocks, ices, and gases over eons. Heavy stuff accretes unevenly, diffusing into hydrogen without a big bang. Lead author Dr. Thomas Sandness nailed it. It's fascinating to explore how a giant planet like Jupiter would respond to one of the most violent events. We see in our simulations that this kind of impact literally shakes the planet to its core, just not in the right way. Impacts fail the fuzz test. They re-stratify too quick. Dr. Louis Teodoro from Oslo adds, the fact that Saturn also has a dilute core strengthens the idea that these structures form gradually during the long process of planetary growth. It's accretion's quiet artistry, not smash and grab. Analogy time. Think stirring batter for a cake. No single dump of flour creates the fluff. It's the slow fold in. This gradual mix challenges old core accretion. Solids don't always clump tidy. They smear, influenced by heat, rotation, migration. Jupiter's youth, a swirling nursery of partial melts and dissolves. Fun fact, simulations clock this at 4 to 5 million years, blinking fast in cosmic terms. But why now in 2025? Juno's finale timed perfectly, validating the shift. No more collision crutch. Fuzz is the default for giants. Speaking of Saturn, yeah, that ringside buddy 648 million kilometers out, its story slots right in. We've probed it too, via Cassini's Grand Tour. Since 2014, ring waves betrayed interior vibes, like seismic echoes on Earth. Pair that with gravity data, and wham! Saturn's no convection free-for-all. Convection's the heat engine. Hot stuff rises, cools, sinks, mixes everything like boiling stew. Full on. The planet's a uniform broth, no dense heart, but Cassini showed patches resisting the churn. Stable layers mean gradients. Heavies pool centerward, feathering out. Exactly fuzzy. Published in 2021, it screamed parallel to Jupiter. Juno echoed non-convective zones aplenty, dots connect. If both ringed and unringed giants fuzz up, it's no fluke. Common recipe in the nebula's outer oven. Old views, solid core plus gas sheath, or total mix? Nah. Reality, Compositional ramps, heavies dissolving boundary-free. This tweaks evolution math. Old models cool giants predictably. Steady shrink, fade. New ones? Chaotic, with fuzz slowing heat escape, prolonging youth. Saturn's rings? Maybe fallout from that uneven brew. Jupiter-Saturn duo hints at a family trait. Exoplanet hunters love this. Thousands of gas worlds out there. Many Jupiter-ish. Fuzzy cores? Standard issue, reshaping habitability odds. Imagine, worlds with diluted hearts, magnets askew, storms eternal. Our duo's the template. But wait, Jupiter's magnetic field? That's the wild card. We've known for ages. Dynamo in the metallic hydrogen sheath, 20,000 to 60,000 kilometers deep. Temps, over 30,000 Kelvin. Pressures, millions of Earth atmospheres. Hydrogen liquefies, electrons roam free. Conductive soup, spin it fast, Jupiter's day, 10 hours, and currents brew fields. It works over time. Jupiter's magnetosphere, monster, 7 to 21 planetary diameters wide, tail snaking 1 billion kilometers to Saturn's door. Tadpole shape, folks, quirks galore. North hemisphere beefier, hot spots punchy, dual south poles. Fuzzy core a fix? Nope, complicates it. Models crave convective swirls for dynamo punch, but Juno flags stable zones, curbing flow. Sims probe, upper stable layer, boosts field fits, lower fuzz, misfires, too tame for observed zaps. Dr. Jacob Kagereis notes giant impacts shape histories, but can't solo explain diversity. So what's cooking? Helium rain, maybe. Droplets piercing hydrogen like oil in H2O, tweaking currents. Or density patches warping conductivity. Earth's field? Uniform hum? Jupiter's? Lopsided roar? Perhaps from core blur feeding uneven spins? Certainty. Auroras on steroids. Hubble's UV snaps stitch eternal polar fireworks. Hundreds times Earth's power. Non-stop glow. Earth's borealis? Seasonal tease? Jupiter's? Cosmic rave 24/7. Breathtaking. Zoom out. This fuzz ripples wide. Gas giants, not simple onions. Cores gradient, evolution bumpy. Exoplanets, over 5,000 spotted, likely echo. Hot Jupiter zipping close, fuzzier still, baked by stars. Implications? Formation timeline stretch, migration messier. Peer-reviewed gems in Nature, science affirm, Juno's 2021 gravity drop, 2025 sims seal it. Challenges: how stable is fuzz? Billions-year lock or slow dissolve? Ties to metallic layer, magnet quirks, open files. But positives: refines codes for alien worlds. SETI dreams: fuzzy hearts mean diverse dynamos, maybe shielding biospheres odd ways. Future? Juno bows out September 2025. 8 years, 70-plus orbits, legacy etched. Next, Europa Clipper, 2024 launch. Eyes icy moon, but Jupiter peaks. ESA's Juice, 2031 arrival teams up. Probing Ganymede, Callisto. Ground Sims ramp, Swift evolves, chasing fuzz bursts. SpaceX Eyes, crude flybys dream, but science leads. Questions linger. Fuzzy universal? Rocky giants too? Your turn. What if Earth's core fuzzed young? Wild, huh? Wrapping up, Jupiter's fuzzy core shatters old tales. Gradual accretion wins, collisions lose. Juno unveiled a diluted heart. Saturn mirrors it. Magnets tease more. Key takeaways. Gas giants brew complex. Exoplanets follow. Exploration evolves. Thought provokers. Does fuzz mean more habitable giants? How's it tweak life hunts? Ponder that. Love this dive into Jupiter's mysteries? Smash like if fuzzy cores blew your mind. Subscribe for space exploration, deep dives. Mars next? Comment, solid or fuzz? What did you bet pre-Juno? Check my black holes vid for more cosmic weird. Thanks for orbiting with me. Clear skies.